Hello everyone, this is Manisai. I'm currently in my fourth year of BTech and now I am presenting a topic marginal probability in the subject of deep learning. So let's get into the topic. So first of all, we go into what is this. We need to know what is marginal probability. So probability of one variable or event without considering the specific value of another variable. Let me one second. It is obtained by summing or integrating over the other variables. It helps us find the probability of a variable when the other variables are unknown or ignored. So relating it to deep learning models often work with multiple random variables. So marginal probability helps determine the probability of one variable from a joint probability distribution. It is used in probabilistic models, Bayesian methods, generative models, and latent variable models. So why is it used? To handle unknown or hidden variable, as I explained earlier, to simplify complex probability distributions, to make predictions when we don't have complete information, helps in inference and decision making, useful for understanding relationships between observed and hidden data. Simple example to explain verbally mean I'll go with. Suppose a model predicts whether an image contains a cat or dog, but there are other hidden factors such as lighting, background, and image quality. So marginal probability allows us to calculate probability of cat without needing to know the exact values of all those other factors. So one line definition is like marginal probability is a probability of a particular variable obtained by summing or integrating over the other variables. So why probability matters is like before understanding marginal probability, we need to understand why probability is important in AI and deep learning. So uncertainty is everywhere. So real world data is rarely perfect and images can be noisy, sensor readings can be inaccurate, and users' behavior can be unpredictable. So probability gives AI models a mathematical way to rep represent and handle this uncertainty instead of making decisions with complete certainty. So joint probability is like P of x comma y. So when we have more than one variable, here we have x comma y. So we have two variables here. So we may want to know the probability of them occurring together. This is called joint probability. For example, if x represents a person having a disease and y represents a person's particular symptom, so joint probability tells us the probability of both events occurring together. So marginal probability. But sometimes we are interested in only one variable and don't care about the specific value of the other variable. In that situation, we use marginal probability. We essentially sum out or integrate out the other variable. Easy to explain, suppose x equal to weather and y equal to whether a person carries an umbrella or not. So joint probability tells us things like P of sunny, comma umbrella. Probability that it is sunny and the person carries an umbrella. But if we only want P of sunny, we don't care whether the person has an umbrella or not. So we add the probabilities of all possible umbrella conditions like P of sun equal to P of sunny comma umbrella plus P of sunny comma no umbrella. That's the basic idea of marginal probability. Marginal probability allows us to focus on one variable by summing or integrating over the other variable. Here, like we did, like if we want to know only probability of sunny, we can do like P of, we can find the joint probability of sunny comma umbrella and sunny comma carrying no umbrella. And now that we understand why probability is important and how marginal probability focuses on one variable, let's look at the basic probability concepts needed to calculate it. So here we can see the probability basics, like what is a random variable. A random variable is nothing but a variable whose value is subject to randomness. Example, x equal to outcome of a dice roll. And discrete versus continuous, like discrete is in the sense countable values. Like examples, we can take finite set of values, like here we can say class labels. And continuous means any real value. Example, temperature. It will not stop at some point. It will go increasing again and again, like we don't have a stop value. Like, and key notations like P of A is represented as probability of A, and P of A comma B is joint probability of A comma B, and P of X equal to X means probability X takes value X. And coming to what is marginal probability, as I explained in the definition itself, marginal probability is probability of one variable regardless of the value of another variable. In simple words, if we have two variables X and Y, but we are interested only in X, so we remove the effects of Y by summing over all the possible values of Y. So discrete case, like we know we have a set of finite values. So point to P of X equals to summation P of X comma Y. Say for discrete variables, we calculate marginal probability by summing the joint probabilities over all possible values of the variable. So here we can see in the slide also. So for example, if X equal to 0 and Y can be 0 or 1. To find P of X equal to 0, we add P of X equal to 0 comma Y equal to 0 and P of X equal to 0 comma Y equal to 1. In the table also we can see we got P of X equal to 0 comma Y equal to 0 as 0.2, and if we take Y equal to 1 we will get 0.3. Similarly, P of X equal to 1 we will get 0.1 comma 0.4. Let me take a laser pointer. So here we can see X equal to 1, and another case is here we are taking here we can see X equal to 1 and we are taking Y equal to 0. So their joint probability is 0.1, and if we take X equal to 1 and Y equal to 1, their joint probability is 0.4, and the total sum of this is 0.3, like and the total sum of this is 0.7. So that is in case of discrete case. If we go for continuous, it goes like there is no summation here. We will integrate like P of X equal to integral P of X comma Y dy. Say when the variables are continuous, we cannot simply add individual probabilities because there are infinitely many possible values. Instead, we use integration. So integrate over y to integrate over y to remove y and obtain the probability distribution of X. A simple way to remember is like discrete goes with summation and continuous goes with integration. Let me move to the next slide. So here, these are the terms I have been using from the slide 2 itself. So joint, marginal and conditional probability. Like, let us consider two variables, weather and umbrella. Like, weather can be rainy or sunny, and umbrella can be we can carry or we cannot carry. So the table shows the probabilities of every possible combination of these two variables. Like, if the weather is rainy and umbrella carry is S, so the probability of rain comma umbrella as S is 0.3, and if the weather is sunny and a person is carrying umbrella, so the probability is 0.15. If the umbrella is not carried by the person, so in rainy weather it is 0.1 and in sunny weather it is 0.45. Each cell is the as joint probability as I explained. So and coming to marginal probability, P of X, point to marginal P of X box. Like marginal probabilities, when we are interested only in one variable, it is as I explained before, and we don't care about the value of other variable. So if we want to find only probability of rain, so what we'll do in this case is we'll find the joint probability of rain comma umbrella carrying gases plus rain comma umbrella carrying gas no. So we have we in this example we took rain as example, right? So we'll take joint probability of rain comma umbrella gases, which is 0.3. We'll add this to the weather gases and umbrella carrying gas no. So 0.1. In this case, we will get 0.4 or 0.4 as our marginal probability. So this is marginal probability. So the probability of rain is 40%, regardless of whether the person carries an umbrella or not. So, and coming to the marginalization process, the marginalization is a systematic process of eliminating unwanted variables from a joint distribution by summing or integrating over all the possible values. That's what we have been doing. And here we can see joint distribution, sum over y, marginal P of X. These are the steps that to be followed to achieve marginal probability. So key intuition is think of marginalization as collapsing a multi-dimensional table into a lower dimensional one by adding up rows or columns. So connection with linear algebra, a joint probability distribution over two discrete variables is naturally represented as matrix. Marginalization becomes a simple row or column sum. So in matrix view, each entry p of I comma j is equal to p of xi comma p of yi, and all entries sum to 1. As we are dealing with probabilities, we can add n number of probabilities and it will eventually result in 1. So here row sum is marginal over x and column sum is marginal over y. In vector notation, it goes like this. And coming to the next slide. So marginal probability in deep learning. So what is the need of this in deep learning? So we can see some of the applications of this marginal probability in deep learning. So one of them is Softmax output, which goes like neural networks output probability distribution. So Softmax ensures output sum to 1, forming a valid marginal p of class or input. So another thing is latent variables. So generative models like VAEs or GANs use hidden variable z. Marginalizing over z gives p of x, the observable data distribution. So and another one is like Bayesian neural networks. So weights are distributions, not fixed values. So predictions marginalize over all possible weight configurations. So coming to an example plus neural network prediction. Now let's look at a practical example of marginal probability in our neural network. Suppose we have neural network that receives an image and needs to classify what is present in the image. Like the first one is like neural network prediction. The image is given as input to the neural network. Internally, the network extracts many features such as edges, shapes, textures, and patterns. So the network then produces score for different classes. For example, suppose our classes are cat, dog, bird, etc. So the final layer uses softmax to convert the scores into probabilities. For example, cat equal to 0.7, dog equal to 0.2, bird equal to 0.1. So the model predicts cat with 70% probability. So why do we call this as a marginal probability? This is the important part. Let's say the model prediction for a class can be viewed as a probability over the class variable, while other internal factors or features are not explicitly shown in the final output. For example, the network may have learned features such as shape, color, texture, edges, background, etc. We don't see separate probabilities for all these features in the final prediction. Instead, the model gives us the probability of the class. So we can think of it conceptually as p of class equal to some are integral over the other variables. For a discrete hidden variable z, p of class equal to, we will use summation here. This is the idea of marginalization. We focus on the variable we care about and account for the variable. So softmax is a thing which converts the network's output scores or log hits into a normalized probability distribution over the class. The connection to marginal probability is that the final class probabilities represent probabilities for the class variable after the network has been processed, the input and its learned representations. And moving to the next slide. So these are all the real world applications and key takeaways. Like first one is image classification, marginalize over pixel uncertainty to predict class labels. And another one is like NLP, natural language processing and speech. Some over unknown word sequences or phonemes to decode meaning. And third one is very important and very used one, medical diagnosis, like marginalize over hidden disease states for probabilistic predictions. And last one finally is recommendations, integrate over latent user preference to rank items. So key takeaway is marginal probability bridges probability between linear algebra, deep learning, AI applications, a fundamental tool for reasoning under uncertainty. So that brings me to the end of my presentation on marginal probability. We discussed what marginal probability is, how it is derived from the joint probability, the difference between joint, marginal, and conditional probability, and its connection to neural network predictions. Thank you for listening. I'm happy to answer any question. Please do drop your questions in the comment box. Thank you.